Next I'm going to talk about a trick for drawing Lewis structures quickly involving bonding preferences and formal charges. So the number of bonds and lone pairs elements of each group prefer to have depends on the group number for that element. So for example, if we look at a 1A element such as hydrogen, it prefers to form 1 bond and 0 lone pairs. A 2A element prefers to form 2 bonds. A 3A element prefers to form 3 bonds. A 4A element prefers to form 4 bonds. When you move to a 5A element, it prefers to form 3 bonds and 1 lone pair. A 6A element prefers to form 2 bonds with 2 lone pairs, and a 7A element prefers to form 1 bond with 3 lone pairs. So as we notice, there's a consistent pattern in the number of bonds that an element prefers to form. It increases from 1 to 4, going from 1A to 4A, and then it decreases, and instead of forming bonds, we have lone pairs instead for 5A through 7A elements. Now, from these bonding preferences, what we can do is we can make a series of building blocks for neutral elements. So for example, hydrogen forms 1 bond, carbon 4, nitrogen 3, oxygen 2, halogens 1. Okay, so now that we have these neutral building blocks that can describe bonding preferences for common elements, we also know that if we think about formal charge, which is the group number of our atom minus the number of bonds plus the number of lone pair electrons, what we can do is we can begin to describe the bonding preferences for charged atoms as well. So using our formal charge rules, we can come up with 3 conclusions, 3 shortcuts. When a bond is replaced by a lone pair, formal charge decreases by 1. When a lone pair is replaced with a bond, formal charge increases by 1. And when a bond is removed, formal charge decreases by 1. So let's look at an example of this. So let's suppose we're looking at the following structure. So this is the for methanol, for example. If we compare this generalized structure for methanol to the generalized structure for methoxide, what we notice is that when we calculate the formal charge for our oxygen atom, we've in effect replaced a bond with a lone pair. The formal charge for oxygen on the left-hand side would be 6 minus 2 bonds plus 4 lone pair electrons. That would give us a formal charge of 0. If we look at the formal charge of our oxygen atom on the right, we see that our formal charge is 6 minus 1 plus 6. 1 bond, 6 lone pair electrons. That gives us a formal charge of -1. A similar example that you can justify via a formal charge calculation is that when we go from ammonia to ammonium, we've replaced a lone pair with a bond, and as a result, the formal charge of nitrogen increases by 1. So these shortcuts will begin to allow you to quickly draw out Lewis structures and will allow you to quickly calculate formal charges when you begin to modify a starting structure. Does this make sense to everyone so far? Does this idea of bonding preferences make sense to everyone? Any questions? Okay, it looks like everyone's comfortable with this, so let's keep going now. So I've made a series of what I like to call bonding motifs. You're not expected to memorize these bonding motifs, but if you're familiar with these bonding motifs for neutral, cationic, and anionic species, it allows you to more quickly write out your Lewis structures. So we have the common bonding motifs for our single bonded structures. And we can also write out a series of bonding motifs for double and triple bonded structures. Now, many of these bonding motifs are related to what are known as functional groups, which is what we'll use later on in this course as a method to even more efficiently draw out Lewis structures. So, what is the benefit of this bonding motif model? Well, it's a very useful method for identifying formal charges quickly and efficiently. So, for example, in the structure on the left, we have a carbon that contains 3 bonds and 1 lone pair. In turn, that bonding motif matches a carbon with a formal charge of -1. We can also separately justify this to ourselves by manually calculating the formal charge and seeing that the formal charge is in fact -1. Are there any other atoms in this structure with a formal charge? Are there any other atoms in this structure on the left with a formal charge? And if so, which atom contains a non-zero formal charge besides oxygen? Nitrogen. So looking at nitrogen, we know that nitrogen currently has 4 bonds. That in turn gives us a formal charge of +1. We can also show this manually by taking our group number for nitrogen minus the number of bonds, giving us a formal charge of +1. For oxygen, which has 4 bonds, we have a formal charge of 0. We can justify this by showing that we take our group number minus the number of bonds, we get 0. So you're still utilizing the basic formal charge calculation. This idea of bonding motifs allows you to more quickly and efficiently assign formal charges. And that's why I like to think about organic structures in terms of bonding motifs. So I'd like you to now, let's take a look at the example on the right. Now, let's take a look at this example on the right. So I'd like everyone to take about 2 to 3 minutes and assign the formal charges to each of our atoms with non-zero formal charges. And then I'd like you to tell me overall, is this structure that we've drawn, is this structure neutral or charged overall? And if so, what is the total charge? But first things first, let's assign formal charges to any of our atoms with non-zero formal charges. And don't be shy to unmute and ask your questions verbally or in the chat. And don't be shy to share your proposed responses verbally or in the chat. Let's try to get a few more proposed formal charge assignments, and then we'll discuss in about another 2 minutes. And the formal charge assignments I see look great so far. Let's try to get a few more responses in the chat, and we'll discuss in about another minute. Okay, so let's look at the following example. So we have a carbon with 3 bonds and 1 lone pair. That would give us a predicted formal charge of -1. We can prove this to ourselves by utilizing our formal charge equation, where we subtract our group number of 4 minus 3 bonds plus 2 lone pairs to give us a formal charge of -1. Looking at nitrogen, so as we can see, nitrogen has 4 bonds. So then we'd predict a formal charge of +1, and we can prove this to ourselves by calculating our formal charge by taking our group number of 5 minus our number of bonds, which is 4, giving us a formal charge of +1. Finally, for oxygen, we see we have 1 bond and 3 lone pairs. So this would give us a predicted formal charge of -1 following our bonding preferences. But we can also manually calculate the formal charge by taking 6 minus 1 bond plus 6 lone pair electrons, giving us a formal charge of -1. Any questions on these examples? Any questions on these examples?
Not for me.
Okay, so we'll continue on with this lecture topic. I'll need one moment just to resize the Zoom chat box. Okay, so let's continue on now, and let's work on a series of examples. So I'll start us off, and I just want to make sure everyone's comfortable assigning formal charge, because identifying sites containing positive and negative formal charges allows us to very quickly identify and notice sites of potential reactivity. So I'll start us off, and I'll do these first 2 examples. So first and foremost, so looking at the following structure, I have a nitrogen with 4 bonds. So I would expect this nitrogen to have a formal charge of +1. Likewise, I have an oxygen with 3 lone pairs and 1 bond. That in turn gives us a formal charge of -1. The carbons in this case, the carbon in this case has 4 bonds. So that gives us a formal charge of 0. And the oxygen has 2 bonds plus 2 lone pairs, which would give us a formal charge of 0. So we've assigned our formal charges to each of our major atoms with a non-zero formal charge. Continuing on, looking at the structure on the right, we have a carbon that has 4 bonds. That would give us a predicted formal charge of 0. And you can justify this again by taking our group number minus 4 bonds, giving us a formal charge of 0. So, looking at this carbon on the left, we see we have 3 bonds plus 1 lone pair. Following our charge preferences rules and following our common bonding patterns, this would give us a predicted formal charge of -1. You can showcase this by taking your group number minus the number of bonds plus the number of lone pairs, giving us a formal charge of -1. So we've assigned the formal charges to all atoms in each of our structures. Now, these structures aren't just chosen randomly. These are commonly encountered bonding motifs in organic chemistry that you should be familiar with and that you will likely see again. Any questions on these representative examples? Any questions on these representative examples? If not, let's now take a moment and let's try to assign the formal charge for a series of compounds. So I'm going to assign these as A, B, and C, D, E, and F. So I'd like you to work on these 6 structures and assigning the formal charge to each atom in these 6 structures. If you've read ahead or if you've tangentially seen organic chemistry before this course, you're going to recognize many of these structures as quite prolific bonding motifs in organic chemistry. So we'll give everyone about 5 to 6 minutes, and don't be shy to share your formal charge assignments for each atom in the chat, and we'll discuss this example in about 5 to 6 minutes. And if you have any questions, don't be shy to ask them in the chat or to unmute and ask your questions verbally. And if you have any questions, don't be shy to ask. And let's try to get as many responses as we can in the chat or verbally, just so that way I can make sure everyone's comfortable assigning formal charges, both either using bonding preferences or the baseline formal charge equation. And the responses I'm seeing in the chat look great so far for structure A. Let's try to get some responses for structures B through F, and then we'll discuss shortly. And the responses I'm seeing in the chat look great so far. Remember, when in doubt, make sure to check your formal charge assignments using the formal charge equation. So let's keep working on this example, and we'll discuss in about another 4 minutes. Let's try to get a few more responses from the rest of the class, or if you have a question on any of these structures and assigning the formal charges in any of these structures, don't be shy to ask in the chat.
Professor, can you scroll down a little bit so I can see number C fully?
Yes, sorry about that.
No problem.
And let's try to get a few more responses in the chat or any questions that you may have. And we'll discuss these examples in about 3 minutes. Part of the reason why I like the bonding motifs organizational structure is because it allows you to very quickly recognize common bonding motifs and assign the formal charges to your atoms very efficiently. And the responses that I'm seeing in the chat look great so far. Let's keep working through these examples. Let's try to get some responses for structures D through F, and then we'll discuss in about another 2 to 3 minutes. And really don't be shy to share your responses in the chat. It helps me get a sense of how the class is doing and if there are any common student questions that I can address moving forward. So let's keep working through this example and then we'll discuss momentarily. And the responses I'm seeing in the chat look great so far. Let's try to get a few more responses from the rest of the class and we'll discuss in about 1.5 to 2 minutes. And if there are any questions I can address during this problem session, I'll be happy to do so at this anytime you have your question. So let's discuss these examples, and I'm going to have the class help me through this. So in structure A, do we have any atoms with a non-zero formal charge? For structure A, do we have any atoms with a non-zero formal charge?
Nitrogen.
Nitrogen, yep. So looking at nitrogen, we see nitrogen has 2 bonds and 2 lone pairs. That would give us a predicted formal charge of -1. We can justify this to ourselves using our formal charge equation of 5 minus 2 plus 4, which gives us a formal charge of -1. Wonderful. So for structure B, would someone like to indicate which atoms have a non-zero formal charge and what is that non-zero formal charge? So for structure B, don't be shy to share it in the chat or verbally. So for structure B, are there any atoms that have a non-zero formal charge?
Nitrogen again.
Yep, so looking at nitrogen, what is the formal charge for this nitrogen atom, which has 4 bonds? The formal charge would be +1, exactly right. Using our formal charge equation, we have 5 minus 4, which gives us +1. Wonderful. Okay. Continuing on to structure C. This is a structure with multiple atoms containing formal charges. So would someone like to volunteer and tell me which atoms have a non-zero formal charge and what is the formal charge for each of those atoms. So looking at structure C, where are formal charges? Sulfur, yep. So looking at sulfur, sulfur has a total of 5 bonds. So we would predict a formal charge of +1. We can prove this to ourselves by taking the group number minus the number of bonds, which gives us a formal charge of +1 for our sulfur atom. Additionally, I notice in the chat that students have mentioned that oxygen, with its 1 bond plus 3 lone pairs, we would predict it would have a formal charge of -1. We can prove this to ourselves using the formal charge equation, where we subtract our number of bonds, which is 1, plus our number of lone pairs. This gives us a formal charge on oxygen of -1. This is a common intermediate in an olefination reaction. So you'll likely see reagents similar to this in organic chemistry too. Continuing on, let's look at structure D for a moment. Let's look at structure D, and I'd like you to tell me, for structure D, are there any atoms with a non-zero formal charge?
Carbon,
And
nitrogen.
could you repeat that, please?
Carbon and nitrogen.
Yes. And what would the formal charge be for carbon, and what would the formal charge be for nitrogen? Carbon -1. Yep. So looking at our formal charge calculation, we'd have our group number of 4 minus 3 bonds plus 2 lone pairs. That gives us a formal charge of -1. And what about nitrogen? I see in the chat, nitrogen has a formal charge of +1. Looking at our formal charge equation, 5 minus 4 gives us +1. This is known as an isonitrile. These are quite smelly, so you don't typically handle them in sophomore organic laboratory, but nonetheless, it's quite an interesting functional group in terms of reactivity. A student had something that they wanted to say. Would you be able to share that with us? Is there a comment that I missed during our discussion? If not, let's look at structure E now. So for structure E, are there any atoms with a non-zero formal charge? Are there any atoms with a non-zero formal charge? This carbon right here. And what is the formal charge for this carbon? What is the formal charge for this carbon with 3 bonds and 1 lone pair? It has a formal charge of -1. Why? Well, we take our group number minus our number of bonds plus our number of lone pairs. That gives us a formal charge of -1. This carbon-centered anion is specifically known as an enolate, and you'll see a lot of enolate chemistry in organic chemistry too. Finally, let's look at the following structure. These reagents are quite interesting. They're known as Wittig reagents. They're commonly used for olefination or carbon-carbon double bond forming reactions. And I'd like the class's input. Are there any atoms with non-zero formal charges in these structures? So phosphorus and carbon. So looking at phosphorus, what would the formal charge be for our phosphorus atom? What would the formal charge be for phosphorus? I have an assignment of +1. So we have a group number of 5 minus 4 bonds. That gives us a formal charge of +1. And for carbon, looking at carbon, we have a group number of 4 minus 3 bonds plus 2 lone pair electrons. And that gives us a formal charge of -1. Perfect. So we've developed this skill of assigning formal charges to structures using bonding motifs or our formal charge equation. This is important because you have to be able to quickly assign formal charges to begin to assess and understand the structure and potential sites of reactivity in organic molecules. So, with that idea out of the way, let's now address this idea of expanded octets. So we'll see expanded octets commonly brought up when we start to look at various reagents utilized in organic chemistry. So expanded octets, quite simply, for n equals 3 and below elements in the periodic table, you have empty available 3D orbitals that can participate in chemical bonding. So in general, for expanded octets, to minimize formal charges, double and triple bonds can be formed that would lead to an expanded octet structure. So looking, for example, at sulfuric acid, if we're just counting our electrons and trying to draw our Lewis structure, hydrogen contributes 1 electron, and we have 2 of them. Sulfur contributes 6 electrons, and we have 1 sulfur. Oxygen contributes 6 electrons, and we have 4 oxygens. So we have 32 electrons to work with. If you were drawing out a Lewis structure in Chem 101 or 102, you'd place sulfur as the central atom, surround it with the 4 oxygens, and place a hydrogen on each of our oxygen atoms. You then form 1 bond each, 2, 4, 6, 8, 10, 12. So we now have 20 electrons remaining. We're now going to assign our lone pairs, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We're out of electrons, and although this structure obeys the octet rule, this structure has a bit of an issue with it. Would someone like to tell me, what do our formal charges look like in this structure? Is there an issue with our formal charges? What do our formal charges look like?
The 2 oxygens have a charge of -1, so we
Yes.
should double bond them to the sulfur.
Yes. In addition to the fact the oxygens have a formal charge of -1, the sulfur also has a large formal charge of +2. So to alleviate this, what we're going to do is we're going to invoke the expanded octet, and we're going to move each one of our oxygen lone pairs down to form a double bond. This in turn reduces the overall formal charge on each of our atoms in this Lewis structure, and overall provides us an expanded octet structure that is more representative of the actual bonding arrangement for sulfur. Does this make sense to everyone so far? Because as we see now, if we look at our
Yeah.
atoms, oxygen has a formal charge of 0, sulfur has a formal charge of 0. So I'd like you to apply this idea, and I'd like you to draw out a valid Lewis structure for periodic acid. This is a common reagent utilized in diol cleavage reactions and other oxidation of hydroxyl groups in organic chemistry. But for now, let's just focus on drawing out a valid structure for periodic acid. And to help everyone just check their work here, to help me check your work, you can either draw your structure using the annotate tool, or you can tell me the number of double bonds in your final answer. Either way, I'd be able to check your work, and I'd like you to spend about 2 to 3 minutes drawing a Lewis structure for periodic acid that follows the expanded octet guidelines and follows formal charge rules. and we'll discuss these examples momentarily. Let's try to get some responses in the chat or some proposed structures using the annotate feature, which is the little pen icon in Zoom. And we'll discuss this example momentarily. And the responses I'm seeing in the chat look reasonable so far. And let's spend about another minute to a minute and a half on this example. And then we'll get started and discuss this example momentarily. Okay, so let's discuss now. So hydrogen contributes 1 electron, iodine contributes 7 electrons, and oxygen contributes 6 electrons times 4, because we have 4 oxygen atoms. That gives us 32 electrons to work with. Iodine is our central atom. In general, your atom that can accommodate an expanded octet will be your central atom in the majority of cases. We're then going to surround iodine with our 4 oxygen atoms and place our hydrogen attached to one of our oxygen atoms. This follows the common convention for oxyacids. What we're now going to do is we're going to form 1 bond each. 2, 4, 6, 8, 10. We have 22 electrons remaining. So now we're going to fill in our lone pair electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, so now even though we've fulfilled the octet rule, if we look at the formal charge of iodine, it has a massive 3+ formal charge, and we have 3 oxygen atoms with a -1 formal charge. So what we're going to do is we're going to move down 1 lone pair from each of our oxygen atoms and invoke an expanded octet structure to minimize formal charges. That in turn gives us the following valid Lewis structure. Remember, the expanded octet rule can only be invoked from elements in the 3rd row n equals 3 elements and below. So here is the complete structure for per iodic acid. Does this example make sense to everyone so far? So let's keep going now. And let's look at another series of Lewis structures for expanded octet structures. So these are common species encountered in organic chemistry. So I'll tackle the first example. So in this case, we have CH2 with phosphorus, and then we have 3 CH3 groups bonded to that phosphorus. Again, if you read through the chemical formula for a compound, it will often provide you descriptive information on the connectivity of atoms and bonds in your chemical structure. So for now, carbon contributes 4 electrons, and we have 4 carbons. Hydrogen contributes 1 electron, and we have 11 hydrogens. And phosphorus contributes 5 electrons. So we have 16 plus 11 plus 5. That gives us 32 electrons to work with. So following our bonding pattern, we're going to place our carbon with 2 hydrogens. we're going to attach that to phosphorus, and then attached to phosphorus, we're going to have 3 CH3 groups. We're going to form 1 bond each between each of our atoms. So we've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. So we have 2 electrons remaining. So then we place our lone pair on the more electronegative atom, which is carbon. And looking at this Lewis structure, it's a reasonable Lewis structure. Is there an issue with this Lewis structure? Is there something that can be improved about this Lewis structure? I see students typing in the chat that I need to form a double bond. Well, looking at our formal charges, carbon has a negative formal charge, phosphorus has a positive formal charge, which is relatively descriptive of how the carbon-phosphorus bond is actually polarized. Nonetheless, to minimize formal charges, we'll move our carbon lone pair down, and in turn, that would give us the following Lewis structure. Again, this is known as a Wittig reagent, and it's used to form carbon-carbon double bonds. And of course, as we can see very clearly from the bonding pattern for phosphorus, we're invoking an expanded octet in this case. Any questions on this example? Any questions on this example? If not, let's continue on. And I'd like you to work on writing valid Lewis structures for the following 3 chemical formulas. So for this first structure, I'd like you to tell me the number of double bonds to sulfur. For this second structure, I'd like you to tell me the number of lone pairs on sulfur. And for the last structure, I'd like you to tell me the number of bonds on phosphorus. So let's take about 4 to 5 minutes, and don't be shy to utilize the annotate feature, which is a little pen feature in the Confer Zoom overlay, to draw out your proposed Lewis structure. Otherwise, take a few moments to draw out a Lewis structure and to try to answer these 3 discussion prompts. And then we'll discuss this example momentarily. You're also, well, if you want to share your drawn structure, you can also share your webcam and in turn hold your structure in front of the webcam, and I'd be happy to provide feedback in that case. And the responses I'm seeing in the chat look reasonable so far. Let's try to get a few more responses in the chat, and if anyone would like to try using the annotate feature, And the responses I'm seeing in the chat look great so far. Let's spend about another 3 minutes on this example, and let's try to get a few more responses in the chat for these discussion prompt questions. And if you're willing to use the annotate feature, I would be more than willing to look over any structures drawn or shared during this discussion. But the responses I'm seeing in the chat look great so far. And if there are any questions, don't be shy to type them in the chat or to unmute and ask your questions verbally. We'll discuss these examples in about another 2 minutes. The central atom is usually the least electronegative. It's usually the least electronegative non-hydrogen atom with a preference given towards atoms that can accommodate an expanded octet. And the responses I'm seeing in the chat look great so far. And we'll discuss this example momentarily in about another minute. Okay, so let's discuss these examples. So first and foremost, looking at this first structure that we have to deal with. Carbon has 4 electrons and we have 2 carbons. Sulfur has 6 electrons and we have 1 sulfur. Oxygen has 6 electrons and we have 2 oxygens. And hydrogen has 1 electron and we have 6 hydrogens. So we have 24 plus 8, which in turn gives us 32 electrons. Okay, so following our structure, we see it's descriptive for the general bonding patterns observed. So we have a CH3 group, otherwise known as a methyl group. We have a sulfur bonded to 2 oxygens, and then another CH3 group. So I've taken the liberty of forming 1 bond each to start us off. That used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we now have 12 electrons remaining. We place those 12 electrons on our oxygen atoms. We are now out of electrons. Now, if we look at our formal charges, as the chat is immediately pointing out, sulfur has a formal charge of +2, oxygen has a formal charge of -1 in both cases. We're now, to minimize formal charges, we're going to move our lone pair down, and that in turn gives us the following valid Lewis structure. This is otherwise known as dimethyl sulfone. And this SO2 moiety is known as a sulfone. We don't see them a ton in sophomore organic chemistry, but it's always important whenever we see a functional group to name it and just start to introduce that vocabulary into our common nomenclature. Any questions on this first example? Any questions on this first example? If not, let's look at the second example for SOCl2 or sulfonyl chloride. So sulfur contributes 6 electrons, Oxygen contributes 6 electrons, and chlorine contributes 7 electrons, and we have 2 of them. So that in turn gives us 26 electrons total. We place sulfur as our central atom, and we surround it with oxygen and 2 chlorines. We then form 1 bond each, so we now have 20 electrons remaining. So from our 20 electrons, we're going to distribute 6 electrons each to our chlorines, oxygens, and our other chlorine. We now have 2 electrons remaining, and our last 2 electrons go on our central sulfur. Although this structure does fulfill the octet rule, as we notice, oxygen has a negative formal charge, and sulfur has a positive formal charge. So to alleviate our formal charges, we're going to move a lone pair down to form a double bond. That in turn gives us the following structure. Don't forget the lone pair on sulfur. This is known as sulfonyl chloride, and it's commonly used as a reagent for oxidation, such as the Swern oxidation, as well as other substitution reactions in which a hydroxy group is replaced with a chloride or other halogen. Any questions on this second example? Okay, so let's look at PCl5, or phosphorus pentachloride. Phosphorus contributes 5 electrons, chlorine contributes 7 electrons, and we have 5 of them. That gives us 40 electrons total. We place phosphorus in the center, and we surround it with our 5 chlorines, and we form 1 bond each. We've used up 10 electrons. We have 30 electrons remaining. And so now what we're going to do is we're going to add our lone pairs. After giving each chlorine 6 lone pair electrons, we've used up all of our electrons, and we have a valid structure. You don't need to necessarily form double and triple bonds. This is an expanded octet structure that has minimized formal charges. Does this make sense to everyone so far? As you notice, most of the examples that we're looking at are very common organic reagents or reagents that you'll see again in Organic Chemistry 1 or Organic Chemistry 2. So knowing how to draw structures efficiently is really a critical skill that we're trying to develop. So continuing on, we're going to talk a little bit next about electronegativity. So electronegativity is a measure of how readily an atom of an element attracts electron density in a chemical bond. Electronegativity increases as you move up on the periodic table and to the right on the periodic table. So an arrow that looks a little bit like this, with fluorine being the king of electronegativity. I provided you a reference hierarchy of electronegativity for common elements to help you rank atoms in terms of electronegativity and quickly compare the electronegativity of common atoms in organic chemistry. This is important because the distribution of electrons in a chemical bond and the electronegativity of atoms in a chemical bond directly impacts how different reagents and organic structures react. Okay. So delving into this idea in a little more detail, electronegativity and most chemical bonds can be thought of in terms of a continuum where we have delta En representing our difference in atom electronegativity. So the difference in electronegativity between atoms in a bond determines whether a bond is ionic, polar covalent, or pure covalent. So common examples of pure covalent, or what we like to call non-polar covalent bonds, have a difference in electronegativity of less than 0.4. You can think of this as an equal sharing of electrons. Examples of this include cases where we have the same atom bonded to itself. So for example, a chlorine-chlorine bond, our difference in electronegativity is 3.0 minus 3.0. You do not need to know the exact electronegativity values. You just need to know the relative values. But in this case, we can clearly see the difference in electronegativity is 0. So we have an even sharing of electrons between both of our atoms. Likewise, in methane, if we think about a carbon-hydrogen bond, our difference in electronegativity is around 0.2. Even though there is a small difference in electronegativity, the difference in electronegativity is relatively negligible. So you can think of a carbon-hydrogen bond as non-polarized or a non-polar bond. Now, where things get a little bit more interesting is if you have a difference of electronegativity greater than 0.4 and less than 2.0, you have what's known as a polar covalent bond. This entails an unequal sharing of electrons. So for example, in carbon monoxide, which looks a little bit like this, ignoring the formal terms, if we just think about how electron density would be distributed in this chemical bond, which atom is more electronegative? Which atom is more electronegative, carbon or oxygen? Which atom is more electronegative? Oxygen.
Oxygen.
Yes, exactly right. So, as a result, if we think about the distribution of electron density in carbon monoxide, we'd likely see a large amount of electron density surrounding oxygen and a very small amount of electron density surrounding carbon. As a result, because oxygen has built up excess electron density, because it has more of the bond's electron density than carbon, it builds up a partial negative charge. We have an excess amount of electron density on oxygen, and we denote this with a delta minus symbol. Likewise, carbon is relatively electron deficient. So as a result, we denote it with a delta plus symbol. To showcase and to indicate the distribution of electron density in polar bonds and polar molecules, we draw what's known as a bond dipole, where our dipole arrow starts at the region that is electron deficient, delta plus, and points and ends at the region containing excess electron density, delta minus. Does this make sense to everyone? Does this look familiar to everyone? Dipole notation indicating regions of partial negative and partial positive charge. So, continuing on, if our difference in electronegativity is greater than 2.0, we have what's known as an ionic bond, which entails the transfer of electrons to give a cation and anion. We commonly see this with organometallic compounds. So for example, methyl lithium, even though methyl lithium is drawn with an actual bonding line, in reality, if we think about our difference in electronegativity, our difference in electronegativity is around 2.1. In reality, rather than there being a formal bond, instead, carbon is so much more electronegative than lithium that rather than having a formal bond, we have an ionic compound where there was a transfer of electrons from our less electronegative metal to our more electronegative non-metal. And instead of having a covalent compound, when you have a difference of electronegativity greater than 2.0, you have what's known as an ionic compound. So methyl lithium can be more appropriately thought of as a carbon-centered anion. So by understanding bond polarity and how differences in electronegativity affect the nature of our chemical bond, we can begin to understand the reactivity patterns for these different organic reagents. That's our goal. Now, continuing on with this idea of bond dipoles, because atoms with different electronegativity values will share electrons unequally, and because our electron density is distributed unevenly, we can denote regions that contain an excess partial charge using delta notation. So in general, our partial negative charge is assigned to the more electronegative element. The arrow for our bond dipole will point towards the more electronegative atom and away from the least electronegative atom. So for example, for hydrofluoric acid, HF, not a common reagent in organic chemistry, at least in sophomore organic chemistry, certainly won't be handling it in the lab due to its pretty prolific hazards. We know fluorine, being the king of electronegativity, would draw the electron density in our chemical bond towards fluorine, and fluorine would begin to build up a partial negative charge. Hydrogen would in turn be relatively electron deficient, and it would have a partial positive charge. We're then going to draw our bond dipole going from our region of partial positive charge, our electron deficient region, towards our region with a partial negative charge, the electron rich region. Now, bond dipoles can actually be observed for different organic and inorganic compounds, because polar compounds will align themselves with an electromagnetic field. We can also see side effects of whether a molecule is polar or non-polar based on solubility and miscibility observations when we start to try to combine and mix organic compounds together, or when we start to try to dissolve an organic compound in different solvents. So we can see how bond polarity and molecular polarity affect bulk physical property. And it also heavily helps inform reactivity patterns. So continuing on, just to apply what we've learned, we're going to indicate the bond polarity for the following bonds. So for a carbon-oxygen bond, that's going to be polarized very clearly towards oxygen. This one's interesting. Carbon-phosphorus bond. Which atom is more electronegative? And this seems like a small piece of trivia, but it comes up in organic chemistry too. Which atom is more electronegative, carbon or phosphorus? And if you have the notes in front of you and you look at the hierarchy, you would think phosphorus. But if you look at the tabulated electronegativity values, and if you look at the common reactivity patterns for carbon-phosphorus bonds, the carbon-phosphorus bond is actually polarized towards carbon, with carbon serving as the more electronegative element. We actually see this based on the fact that carbon-phosphorus bonds function more similar to a carbon nucleophile rather than a phosphorus-based nucleophile. It really shows how subtle changes in an atom can result in pretty dramatic changes in potential reactivity. So what I want everyone to do now is to look at the following 3 bonds, and I'd like you to indicate the more electronegative element where our bond dipole arrow will point in each of the following bonds. and we'll discuss this example in about 2 to 3 minutes. Again, looking at each of these indicated bonds, we're going to indicate the more electronegative atom in each of these bonds. And you'll submit your responses in the chat or verbally. And if you have a question, don't be shy to ask it in the chat or verbally, and I'll be happy to address your questions. The responses in the chat look reasonable so far. Let's try to get a few more responses in the chat, and we'll discuss in another minute. And the responses I see in the chat look great so far. So let's discuss. So for our carbon-nitrogen bond, nitrogen is more electronegative, so our dipole will point towards nitrogen. For our sulfur-oxygen bond, oxygen's more electronegative, so our dipole will point towards oxygen. For a carbon-magnesium bond, carbon is more electronegative, so this bond will point towards carbon. In reality, this isn't a formal covalent bond. It can best be thought of as an ionic pairing between a carbon anion and a magnesium cation. Does this example make sense to everyone? Does this look familiar from general chemistry?
Yeah.
Perfect. So we've built up a lot of foundational skills. And now what we're going to do is we're going to review aspects of valence bond theory and molecular orbital theory that you'll need for organic chemistry. So we'll introduce and we'll start this topic today, and we'll finish this topic in depth next session. So let's talk a little bit about valence bond theory and the key tenets to help us explain chemical bond and chemical bonding patterns. So a chemical bond consists of an electron pair shared between atoms. Now, in valence bond theory, a chemical bond is formed by the overlap of two half-filled atomic orbitals or hybrid orbitals. So we have our two half-filled hydrogen 1s orbitals overlapping to form a bonding molecular orbital. Okay, two half-filled orbitals overlap to form a bond and a bonding orbital. Now, there are two types of bonds, the first of which is a sigma bond. It's an overlap of atomic or hybrid orbitals directly between the bonded atoms along the bond axis. So for example, our sigma bond in this case is our overlap directly on the bond axis. I like to think of sigma bonds as our single bonds. I like to think sigma single. The other type of bond, which props up primarily when we start to look at double and triple bonds, are our pi bonds. Pi bonds include the overlap of unhybridized p orbitals perpendicular to our bond axis. So pi bonds overwhelmingly involve the overlap of p orbitals. I'm just also going to put in parentheses, and d orbitals can also form pi bond-like bonding arrangements, though p orbitals are far more common. So as we notice, the pi bond is an overlap perpendicular to the bond axis. So for example, in this case, I like to think of pi bonds. When I see the word pi bond, I like to think are double and triple bonds. So for example, an oxygen-oxygen bonding arrangement consists of a single bond. So our single bond would be our sigma bond. So that's our single bond. And then our double bond would be our pi bond. So bonding patterns will utilize sigma and pi bonding overlap patterns. So to continue on, let's now introduce this idea of molecular orbital theory. And a central tenet in molecular orbital theory is the idea that the overlap of atomic orbitals or hybrid orbitals will yield a bonding molecular orbital and an anti-bonding molecular orbital. So our bonding orbital is noted by sigma 1s plus 1s because we've overlapped two 1s orbitals. So this is our bonding orbital that we're so familiar with. And we also have an anti-bonding orbital. And this anti-bonding orbital is known as a sigma star orbital. And this is the anti-bonding orbital formed from our two 1s orbitals. So we put two orbitals in, and in turn, we get two orbitals out. So when we overlap our half-filled atomic orbitals, we get a bonding and anti-bonding molecular orbital. And this in turn directly influences the bond strength, and it also indicates the location of potential sites for reactivity. This sigma star orbital, as we notice, takes up three-dimensional space, and it is accessible for chemical reactions and serves as a site of potential chemical reactivity. So when atomic orbitals overlap, we place our electrons first in the lower energy bonding molecular orbital. So if we're forming a hydrogen-hydrogen bond, so we'd take our hydrogen 1s orbital and we'd overlap it with another hydrogen 1s orbital. We get a bonding molecular orbital, and our anti-bonding orbital, which we know sigma star, is empty. Now, you may have noticed that different colors are clearly noted in our anti-bonding orbital. We'll touch on this later, but these colors imply different orbital phasing. In other words, when we try to engage in an anti-bonding interaction, we observe what's known as destructive interference. So we're not sharing electrons between atoms in our anti-bonding orbital. Rather, there's no electron density at all shared between our atoms. Okay, so this is the basic premise behind valence bond theory and molecular orbital theory. Let's talk a little bit now about how different types of orbitals can overlap and what kind of bonds each of these orbitals can form. So for our s orbitals can overlap to yield sigma bonds. So So they can overlap on the bond axis and yield sigma bonding orbitals and anti-bonding orbitals. In the case of p orbitals can first and foremost overlap to yield sigma bonds. So they can overlap directly along the bond axis to yield a sigma bond and an anti-bonding orbital. Alternatively, p orbitals can also overlap to yield pi bonds, where they overlap perpendicular to the bond axis. And just like sigma bonds have bonding and anti-bonding orbitals, pi bonds also have bonding and anti-bonding orbitals. Again, notice for our bonding interactions, the overlap occurs between regions of the same phase. This is why orbital phasing is really critical. Now, because there are two different types of p orbitals, we can in turn form a total of two different pi bonds. In summary, two atoms can form a maximum of one sigma bond and up to two pi bonds between our atoms using this model. Now, you know from the octet rule and from the Lewis structures that we've drawn, we can generate more sophisticated structures. And that begs the question, how do we utilize our atomic orbitals in order to maximize bonding and minimize our electron energy? Well, we'll introduce this idea before we finish today, and we'll pick up on this next session. The way that we maximize bonding and we minimize our electron energy by forming chemical bonds is through a process known as hybridization. Now, we know that to form a bond following these rules based on valence bond theory and molecular orbital theory, the two orbitals that we use and overlap for our chemical bond must be half-filled, they must have the proper geometry, the proper three-dimensional arrangement, and they must be close in energy. So, if we think about methane, if we look at carbon, so carbon, we have a 2s and 2p orbital that contain our valence electrons. And we know carbon has 2 electrons in its 2s orbital and 2 electrons in its 2p orbital. So then, in terms of the maximum number of bonds that carbon can form under the current orbital arrangement, how many half-filled orbitals does carbon have? How many bonds can carbon theoretically form with this current electron configuration? How many half-filled orbitals does carbon have? How many bonds can carbon potentially form? 2. So under our current model, we can form 2 bonds utilizing our half-filled p orbitals. Now, we obviously know that carbon can form more than 2 bonds. However, under our current electron configuration, our electrons are either distributed into full orbitals, or our electrons are in an orbital that is not geometrically set up for bonding. This 2s orbital is geometrically not very convenient for forming chemical bonds. So what we're going to do in hybridization, we're going to combine our atomic orbitals to give hybrid orbitals with the average geometry and energy, and with an optimized geometry and energy for chemical bonding. So we're going to take our s orbital And we're going to combine and hybridize it with each of our p orbitals to form new, what we like to call hybrid orbitals. And in this process, if we undergo for example, an sp3 hybridization, we're going to average out the energy and geometry of our s orbital and our 3p orbitals. That gives us, if we take 4 orbitals and we hybridize them together, we get a total of 4 hybrid orbitals. Of the same energy. And these sp3 orbitals, as we begin to notice, they have a very different geometry and shape than our p and s orbitals individually. Additionally, and this is the critical part, this is the really critical part. Now, considering that we now have 4 sp3 orbitals, if we started with 4 electrons, where are those 4 electrons going to go? Where are those 4 electrons going to go? We start with 4 electrons before hybridization. Where do we place our 4 electrons now? Where are remaining electrons going? So if we are filling in this orbital box diagram, if we have 4 electrons to start, we will end with 4 electrons. And now, if we place our 4 electrons, what do we notice now? How many half-filled orbitals do we have that are able to engage in chemical bonding? How many half-filled orbitals do we now have? 4. So we have 4 half-filled orbitals. So hybridization serves not only to generate orbitals with the correct geometry, the correct 3-dimensional shape for bonding, it also allows us to generate half-filled orbitals that are capable of engaging in orbital overlap and engaging in bonding interactions. Now, this is really critical because the molecular geometry is directly determined by the shape of this orbital overlap. So what we're going to study in detail next class session is how hybridization occurs. We're going to look at the different shape of each of these hybrid orbitals and energy of each of these hybrid orbitals. And we'll talk a little bit about how to describe chemical bonding using this valence bond and molecular orbital model. So this short discussion is a teaser for what we're going to be unpacking in detail next class session. So we're going to pause the lecture recording for today.